Okay, so let's talk about energy effects in forming binary ionic compounds. This pertains to section 3-4 in your textbook. Um, in the previous lecture, we had talked about how to form an ionic solid from its component elements in their pure states, their so-called pure states. So the example that we had used was the formation of the salt sodium chloride from its component elements, sodium and chlorine, in their pure states. Now, uh, metals in their pure states generally are solid, neutral, monoatomic elements. So sodium is just solid sodium here. Halogens in their pure states are diatomic, and chlorine is a diatomic gas in its pure states, and that's just something that we know. So something that I'm telling you for now. Now, if I have solid sodium and one half of a molecule of chlorine gas, I can write a balanced equation to produce NaCl solid. So now I want to break this reaction down and consider all of the processes that would be involved in producing that salt, in producing that ionic solid from its component elements in their pure elemental states. And we can do that using a cycle of reactions called the Born-Haber cycle. And this is actually a cycle of both physical and chemical processes. So I have written down a bunch of processes that are involved in transforming those elements in their pure states into the ions that are involved in the ionic solid. So I want to consider now the energy change associated with each of these processes. So they're both physical and chemical changes. And the first one involves taking solid sodium and just turning it into a gas. That is a physical change. That's a phase change. And you may know the name for that. When a solid transforms into a gas, that process is called sublimation. And the delta E associated with the sublimation of sodium is positive 109 kilojoules. Now, the sign is very important. When we put energy into the process to make it go, it has a positive sign, a positive energy. And it makes sense because if you think about it, you would need to put energy into a solid to make it vaporize, right? To turn it into a gas. That would seem to require energy input in the form of heat. So we denote that using a positive sign for the energy change. Let's look at the next example. We have sodium gas losing an electron. Now, we've seen that before. That's ionization energy. And the ionization energy is also positive. In this case, it's a large positive value, 493, because it requires energy input into the system to ionize that electron, to pull that electron away from the sodium atom. We also have the diatomic chlorine molecule. Now, in this reaction here, I am ripping that molecule apart. I am breaking the bond between the chlorine atoms, so I have just chlorine all by itself. Breaking a bond is also known as dissociation. So dissociation literally means breaking a bond. And it requires energy to break a bond. So this is also a positive value, 121 kilojoules are required to break that bond. Now, if I want to then take that gaseous chlorine and add an electron to it, we have seen that one before. That is the electron affinity, adding an electron to an element. And electron affinity is essentially the opposite of ionization energy. So it has a negative sign. And the negative value for that for chlorine is minus 364 kilojoules. Finally, I have the gaseous sodium and chloride atoms packing together to form the ionic solid. And we've talked about that before as well. That's the lattice energy. Lattice energy is defined as the energy that's released when gaseous ions pack together to form a solid. So energy is released from the system when that happens. So this gets a big negative value. And it's a large value because lattice energy tends to be large and negative. You have a lot of energy released when gaseous ions pack together to form a solid because that's a very favorable process. Now, what I would like to do is look at all of these reactions and add them together and see what we get. And I also want to add the energy changes together. Just like in mathematical equations, if I'm adding things together and I have species that are the same on both sides, I can cancel them out. So I can cancel out the gaseous sodium ions and sodium atoms as well. So these species can be canceled out because they're the same on both sides. Chlorine atom, the gaseous chlorine atom can be canceled out. The single electron can be canceled out. And the gaseous chloride ion can be canceled out. So after I do all that cancellation, the only things that are left are sodium solid plus 1/2 of chlorine gas, giving me sodium chloride. And you'll notice that that reaction matches the reaction from before, producing sodium chloride from its component elements in their pure states. Now, if I want to figure out the energy change associated with this, I have to just add up all the values from this column over here. So I have positive 109 kilojoules plus 493 kilojoules plus 121 kilojoules minus 364 kilojoules minus 770 kilojoules, just adding up everything with their respective signs in that column. And that gives me a value of minus 411 kilojoules. This is the energy released when sodium chloride solid is formed from its component elements in their pure states. And it makes sense that it's negative because we're lowering the overall energy of the system. It's a favorable process because you're creating all of these ionic bonds that are very favorable interactions between the positively and negatively charged ions.